folks. Sorry, I got a frog in my throat. Today we're going to start with section 9.5, which is more the usual sort of thing that you would do in an algebra or trig class, which is to solve equations. Right? In this case, it would be trig equations, though, as opposed to algebraic equations. The good thing is that a lot of the rules that we have already established in terms of solving an algebraic equation do translate to this. Right? The only thing I would advise you to do up front is have certain diagrams on hand while you're going through this. Right? First would be good is this old diagram, right, for solving quadratics. Factoring in particular and taking advantage of the zero product rule is especially helpful, and potentially the quadratic formula, these two. And if you feel a little rusty with factoring, don't feel bad. All right, again, have another reference on hand. It's the same one, sorry. Factoring techniques. The models, difference of two squares, perfect square trinomial, they come up frequently, and the general AC product pairs in tandem with factoring by grouping. Right. Those are algebraic diagrams that are good to have. Now, as far as trig diagrams that are good to have on hand, there are two. Right. This one, again, not to beat a dead horse. Right. This diagram is very helpful because it shows the relationship between normal degrees and pi radians, right, around a complete 360 of a circle. Right. And lastly, the established identities from last time are good to have, right? Especially these reciprocals. If you're given something like cosecant, you could just translate it into sine. And secant similarly will translate it into cosine. Okay. All right. And of course, your calculator. Now, here's just a thing to remind you. I wrote here to start with. All right. Because trig functions are periodic, which means that they're cyclical, right? Especially sine and cosine is the most obvious, right? Because they're a wave in the classic sense. We are frequently asked to solve over a specified interval, right? And I drew this kind of cheesy interval notation around the word interval to emphasize that point, right? Normally, remember when you have an interval notation, it's specifying, okay, you're going to look in a certain spectrum of possibility along a number line, or in the case of a wave, along the medium of the wave. Now, what are you actually solving for? Right? Well, if it involves a trig function, probably an angle. All right. And again, if necessary, there are times when we could translate that into something that is a little bit more algebraic, maybe for the sake of factoring. All right. This is just an example of what I mean by periodic. Remember, the period of a sine or a cosine is normally 2 pi, right? And what that really means is that the y values repeat, right, between the boundaries of positive 1 and negative 1, right? Positive 1, negative 1 towards infinity, right? So you can't do something for the rest of your life, all right? You'd never finish, all right? If they said, oh, give me all the possible answers, all right, you'd have to narrow your scope, right, to a certain spectrum, a certain interval namely, okay? What you will do a lot is draw diagrams. Let's see. Let me erase this because I need the space. Diagrams of a unit circle and a right triangle inserted inside of it. Inscribed, I believe, is the phrase. So here's an example to get your feet wet. All right. Find all possible exact solutions. for this trig equation. Put this in a different color. The cosine of cosine of theta equals 1/2. Okay. Now again, this is just to emphasize that there really is an infinite number of solutions to this. All right. Potentially are. Let's see. At least more than one. Let's start by dissecting this. Okay, here's your trig function. And remember SOHCAHTOA, all right? The ratio of which cosine relates, all right, or is derived from, or is referring to. Cosine is on top the adjacent dimension over the hypotenuse, all right? And if you were going to translate that, I actually did myself a little favor and I made a template finally. Let's see if this works. It's probably going to be a little too cheesy, but you know, we'll do this. I guess that's appropriate to come from a pizza box. Okay. There's a slightly better circle than I normally draw. Okay. If you were to take a unit circle and translate this, not the best straight line here. These dimensions, right, of adjacent and hypotenuse into something that is a coordinate plane's dimensions of x and y and r superimposed upon a unit circle. Let's draw a triangle inside of it in standard position. Remember, when you draw a right triangle, draw the y dimension of the triangle perpendicular to the x-axis always. Otherwise, you're not going to be drawing triangles like this. Right? We're always going to have them oriented as y dimension perpendicular to the x-axis from here to here, from here to here, or from down here to here, or from down here to here. Right. Okay. Here's a right triangle. Okay. If, just assuming to get started, this is in standard position, right? Your angle of theta would be here, all right? In terms of what is respect, let me rephrase that. In respect of the angle here, what would be adjacent would be the dimension this way, all right? But that is better known as x, right? So this is an x, right? In respect of the angle in terms of this dimension, hypotenuse would be here, right? And if this is part of a unit circle, connecting the center to the outer edge of the circle, this is referred to as a radius. So this is an r dimension. Right. Now, considering that this is a positive 1/2, right? In theory, all right, there's more than one, maybe perhaps not infinity, all right, but there's more than one possibility for the angle here, given these dimensions, all right? For this to be positive, all right, you would have to have a positive x, all right, in this case, all right? The r dimension, the hypotenuse radius, whatever you want to call it, is always positive. Right. That means essentially that it's either x or y that could be negative, you know, in a different problem. In this case, it started out as a positive, presumptively, all right? There was no sign given, you could assume that, all right? But we don't have any other information. We really don't know what specific interval, because it's not specified. So there is another possibility here. I'm going to simplify this drawing to take out the unnecessary information at this point and just illustrate the x and r. Right? This is the positive x dimension, right? Heading off in this direction. This is r, right? But we don't know anything about y, right? Y in this orientation is a positive y. Anyhow, what is possible is that we could not just be referring to this specific triangle, but this one instead, because it still conforms to the same conditions. The radius r is always a positive, or you could say it has no sign if you would prefer. It is either the x or the y that has to be a positive or a negative dimension. All right, and in this case, notice that they share this x dimension. These two triangles both have the same x. And it has to be a positive because it is in the first quadrant, and technically this endpoint here, this corner, the edge of the circle is in the fourth quadrant or the first. Okay, so that means that you're going to get, at least assuming that you're just sticking with one complete circuit, one period of 2 pi, 2 possible angles here. How come? Because there's this original angle that's just stretching from here to here, and then there is the angle that would go all the way this way, all right? That would produce this negative incarnation of the same angle. Okay, so for the first angle, all right, given a cosine, and these are the dimensions of 1 over 2, all right, there are, this comes from the famous 30, 60, 90 right triangle. Let me erase something because I need the space. Remember, we have 2 special right triangles that are good to know by heart. The 30, 60, 90, and the 45, 45, 90. Right. If this is the orientation of 30 here and 60 here, all right, then the dimension along the bottom here would be square root of 3. The dimension along 60 here, 90 is 1. And the hypotenuse would be 2. The 45s are 1, 1, and the square root of 2. Anyhow, you, given 1/2 and recognizing that this is referring to a hypotenuse, would gravitate towards looking at this, right, rather than that special right triangle. Okay. The thing is, the orientation of the angles is normally given as 30 along the x-axis, right? And in this case, right, what do we know our x value is? It's 1. Right. What that means is that this is actually a rotated incarnation of the special right triangle. like so. It would be the 60 this way and the 30 this way. Even though that's not how you usually memorize it, that's really what it would equate to. Along the edge that is 30 and 90, all right, is always the square root of 3. Along the edge of 60 and 90 is always 1, and this is 2. In order for this to be an x dimension, all right, and adjacent, all right, it would have to be a 60-degree angle that is actually here. This is, although a bit convoluted and it takes some getting used to, all right, it is a way of inferring, all right, what the angle ought to be, all right. So that means that this is, at least to start with, 60 degrees. If this is theta, and that's really the unknown, this is 60 degrees, right? This is your R, and this is technically what your Y would be. Okay, now, could you do this with your calculator? Absolutely, but the thing with your calculator is it's not going to give you the other possibility, which is why you would need to draw a picture, and also to memorize some fundamental facts, right? Right. Here's what you would do, right? If you were using your calculator only for a problem with like this, right? First of all, you would need to set it to degree mode potentially, and then use an inverse function. So if we're talking about cosine of theta equals 1/2, you would have to say you would have to type this, the inverse cosine of 1/2. When you find inverses, they give you angles, right? So you would type this, right? I'll show you really quick. All right, and then we'll do the other one. All right. Okay. So you make sure this is in degree mode. It's in degrees. Quit. Okay. And you will hit second and then inverse cosine. And you could type 0.5 or you could just do 1/2. Right. I'm going to be fancy, so I'm going to put it in the intuitive fraction-esque style of typing 1/2. That is the one sitting at the top and the 2 on the bottom. You don't have to do it that way, but I think it makes it more intuitive. 1//2 would also work, right? The inverse cosine of 1/2 would naturally tell you what the angle ought to be given these conditions for x and r. And it gives you 60 naturally. Now again, the problem with this, although it is handy, and I would do that, is that it's only telling you this condition, this situation, all right, the most basic, all right, dependent upon trig ratios and special right triangles, that this would have to be a 60-degree angle here. All right. What you would need to do, all right, is just acknowledge the fact that since this was positive, that this is referring to an x, and this x is the positive x. All right, the bottom of each of these triangles, so the bottom here, the top, and in this orientation, all right, these are where positive x exists in quadrant 1 and in quadrant 4. All right. All right. Again, since nobody specified an interval in which we had to look only, like to say, oh, only between 0 and pi, you know, then that would be the only answer then. If they said every exact solution, I would at least limit it to 1 complete rotation, 360. So the normal period of 2 pi, right? Which means that is another possibility. Now, how do you figure that out? If you have the angle of 60, you could just do, 360 minus 60. Right? The angle that would be here is a negative 60 degrees if the angle here is a positive 60 degrees. Remember that we read counterclockwise normally. Let me erase this, I need some space again. I'm just going to duplicate what was the original problem because I hate to erase things like that. And we have discovered that the theta, the angle, is actually 60 degrees. Well, again, if you have a reference, I mean, you could just look at this reference. I'm just going to flash it really quickly. And see what 60 would correlate to in the fourth quadrant down here. All right? No sin in that, it's reading, you know. But let's figure it out. Right, the mental exercise is important. So, if we're trying to figure out what this angle is, and you know that a complete circuit is 2 pi, otherwise known as 360, 360 degrees minus 60 degrees. Is 300. From the point of 0 degrees here, rotating through here, you would have 300 degrees in the normal way you would read it, the counterclockwise orientation. All right? 300 degrees is the equivalent of negative 60. So here's one possibility, which your calculator can validate. Here's what the other possibility would have to be, right, for this angle here. And then the last thing is that probably what will be given or asked of you is to put this in pi radians, right? When they say exact solutions, right, they probably mean pi radians. As opposed to full-blown radians, right? Because if you just go the whole 9 yards for just radians strictly, you're actually incorporating 3.14, right? Rather than simply leaving the pi symbol. So what you would have to do is translate 60 degrees and 300 degrees to the proper number of pi radians, right? You know how to do that, but let's review it. Now I'm going to erase this. You use a conversion factor, right? So the green is okay. That's not bad, okay. If you are given something and you multiply by the appropriate conversion factor, that will give you what you want. In this case, sorry for the sloppiness, if you are given 60 degrees, and that would go here. And you want to convert it to pi radians, right? What you're going to need to do is to rig the conversion factor, and there's only 2 versions of this, right? There's only pi over 180 or 180 over pi, right? You're going to rig it so that there's a cross cancellation effect, right? And that will leave you with a certain fraction of pi, right? So if degrees is up here and I want to cancel out degrees, it would be more appropriate to put 180 as a denominator, right? And leave the pi symbol up here. When you have a whole number, like 60 degrees, you could disguise it as a fraction very easily, just to do the ordinary top times top, bottom times bottom style of arithmetic for fractions. And this is the effect. This degree symbol would be canceled by this because they are across from one another diagonally, one above the line, one below the line. It's like dividing without consciously thinking about it. You could simplify the fraction up front. That would probably be the strategic thing to do. But let's say that you didn't, right? Let's say that you just went, all right, it's 60 sitting on top of pi over 1 times 180 is 180 over pi. This fraction could naturally be reduced. All right, pull some tricks. You can enter it into your calculator, and your calculator can certainly handle it, but pairs of zeros, you can cross them out. It is like dividing by 10 without really consciously thinking about it. And it has the same relationship of 6 to 18, which if you know your multiplication tables of 6, right, you recognize as there being a relationship there. That is to say that 6 and 18 are made of the same factor, which is maybe weird to say, but it's 6. That's the GCF. 6 divided by itself is 1. 18 divided by 6 is 3, which means that this is pi over 3. All right. Again, if you have the reference diagram, sometimes I have 3 sticky notes that just don't stick. You could confirm that. Here's 60, that's pi over 3. Now, if you trace this green line, right, you'd see that directly opposite of that would be 240. But in the fourth quadrant here is 300 degrees. You will find that the appropriate pi radians for the possible negative 60 or 300 degrees is going to be 5 pi over 3. Right? Let's just do the calculation, for argument's sake. It's a good mental exercise. We know what we should get, and it helps to validate. Okay. I'll move this. Okay. This one is, again, you're given degrees, and you're going to choose the appropriate conversion factor, and that will give you what you want. So if in this case, I would go with this dimension 300, because if you went with negative 60 in this case, it's just going to give you negative 3 pi, right? Which is not the normal way to write it, right? Perhaps not the preferred way to write it. So 300 degrees, again, you're going to rig it as pi over 180 for the sake of cancellation of the unit degree, which is a naught superscript. And then you get this, 300 sitting on top of pi. This is top times top and bottom times bottom. And then you can pull tricks. Right. It's usually when they teach you arithmetic when you're a kid, right? Especially fractions, they try to get you in the habit of cross-simplifying before you multiply. Reason being that once you multiply, it's going to make things larger. And when things get larger, numbers get larger, they start to be outside the realm of what is familiar. So it would be more strategic to simplify first. But it is possible to simplify after the fact. Anyhow, cross out a pair of zeros. It's like dividing by 10 without thinking about it. There's a relationship between 30 and 18. Right? They're both divisible by 6 once again. All right? That's their GCF. 18 divided by 6 is 3. 30 divided by 6 is 5. That means that you have this as the other potential angle. To summarize, this is what we calculated. We solved for theta, and we discovered that it was 60 degrees according to special right triangles, right? And that is pi over 3 in the style of radians. But then we acknowledged that since we weren't given any other information, it is possible for this to have been negative 60 degrees, right? Which itself can be written as 300 if we were to read counterclockwise versus regular clockwise. Negative 60 is reading clockwise, right? 300, which would probably be preferred, is counterclockwise, which is ironically perhaps the way that we prefer things. Anyhow, if 60 is pi over 3, 300 is 5 pi over 3. all right? These are two answers that you can get, all right? All right, in theory, they didn't specify an interval. It would be another, if you added 2 pi to 60, all right, you can have another angle of whatever 60 plus 360 is, 420, all right, is another angle, and express that in terms of radians, and there would be infinite answers, but that's sufficient for right now. All right, anyhow, just please remember, you could rely on your references, right? As long as you can identify the 60, a 45, and a 30, you could use this to validate pi over 3, pi over 4, pi over 6, respectively. And these are the things that would theoretically be possible for those. In our case, it was these two that are in green. Okay. All right. That's kind of a review of all this stuff anyhow. Anyhow, you would have infinite solutions at coterminal angles, right? 420, which is what 60 plus 360 would be, is coterminal. Right? 420 degrees is coterminal to 60 degrees. Let's see. Let's do another. Again, don't feel bad about using your calculator, all right? And this is I'll leave this here. But just realize that there are more than just the answers the calculator gives you, because it's periodic. Let's say you finally are given some better conditions. All right. An example would be the cosine of 30 minus 3 is equal to -5. And a lot of times they'll specify that your angle of theta has to be in this interval. It's not written in interval notation. But it can translate to that, right? This is using inequality symbols. Another way of writing this in interval notation would be equals is a bracket, so 0 would be included. And 2 pi would be the limit, but you don't include that. Right? It just so happens that 2 pi is 360 and 3 and 0 overlap. But anyhow, they don't want you to exceed really 360. Right? I mean, looking for possible answers to this angle. I'm going to put this in red because I want you to sort of zero in on that. This is the variable. Without it being explicitly stated, this is the variable, all right? So therefore, this is what you're looking for. You're looking for an angle, all right? Now, how would you go about doing it? As I mentioned before, the old tricks still work, all right? The algebraic tricks that you had learned from years ago, all right, are still going to work. You're basically, the objective here is to isolate the variable to one side. So if you're going to isolate the variable to one side, it doesn't matter if it's right or left of equals. That means that you're basically going to isolate the trig function to start with. because that's where the variable is attached. Now, how do you isolate things? You only have to move stuff around. Do perform opposite operations. And then to make it legal, do to both sides of the equal sign. Sorry, it's a little bit sloppy. Does that help? I don't think it does. I think it's better without flags. Alright, so as always, draw a table. These are opposite sides of equals that we're going to move stuff around. And when you're solving equations, remember that you do the easier thing first. You do the adding or the subtracting first, usually. So I'm going to drag 3 from over here to the opposite side. All right. And then I'll move 2. The opposite of adding 3, pardon me, of subtracting 3 is to add 3, right? Opposite operations, do it to both sides of the equal sign. All right, that's what makes anything legal. You can get away with murder in math as long as whatever you've done here on the left, you do here on the right. It's a balancing act. All right, there is intentionally a cancellation effect. All right, and that leaves you naturally with just this stuff. 2 cosine of the angle is equal to the outcome here. All right, if you have -5 plus 3, one of each sign dictates that you subtract, which means that you're going to get a 2, and it will match the sign of the bigger magnitude, so it's -2. Okay. Last thing is second to last thing is to move the coefficient. As you know, right, when 2 things are pressed together, it is implied that they are being multiplied. So if you wanted to justify moving the 2 from where it is over to the opposite side, you would do division, because that is the opposite of multiplication. If you did it here, you're obligated to do it here. There is again a cancellation effect. This is my dud, okay. And then you have this, the cosine of the angle, which I again prefer to write in red for the sake of emphasis, is equal to the outcome here. If this is -2, essentially divided by +2, the multiplication/division set of rules for integers takes over. So you will have a negative answer, all right, and this would be equal to -1. All right. Now a couple of things, all right. At this point, you totally can do this, all right. You can go, all right, if I'm looking for an angle, what gives me an angle? All right, inverses. Calculate angles. So if you wanted to enter this into your calculator, this would indeed give you a viable solution. That will be what the angle is, the inverse of -1 because of the arithmetic. All right. And you'll see what it is. All right. But as a backup, all right, what I would suggest you do is draw a simple diagram. All right. It is good to internalize some information, memorize some basic fun facts about cosine, sine, right triangles, stuff like that. Here's what I mean. I'm going to erase everything above this. And draw a very simple picture to remind you. There's a little thought cloud. We know at this point that a cosine unraveled over the interval of 0 to 2 pi would basically oscillate, periodically repeat, all right, in this interval. All right, it would start at +1 and it would end at +1, but it would go through this cycle like so. These points are good to know by heart, aside from that this is the cosine shape in this interval. the interval of 0 to 2 pi. If you have that memorized, right, and you know that the maximum is going to be positive 1 and the minimum is going to be negative 1, you could basically look for where it's negative 1, right? If this is an x, then this is a y. So go to the point of negative 1 in the drawing, right, and go to the point of where it actually touches the curve, right? At negative 1, y, and these are all x's, you're at what location, right? In this interval of 0 to 2 pi, you're at the location of pi, right? Which means that's what I predict the angle is going to be. Right. The actual angle here, let me just recognize color, should be this, 180 degrees, otherwise known as pi. Right. Unfortunately, a calculator can only give you radians, which means you'll get the decimal 3.14, 159, whatever the precision is. Or if you have it in degree mode, 180, right? It's not, unfortunately, unless you maybe have an amped up super duper calculator, it's not gonna go, pi, all right? But you do know how to convert from this to pi radians, and you do know that pi is 3.14. Anyhow, let's enter the inverse cosine of negative 1. Right now it's in degree mode still. So the inverse cosine is second and then cosine. And then you put, be careful again, here's that instance where you have to use this to make it a negative coefficient. 1, close the parentheses just to be twitty, right? And you get 180, okay? If in theory you had this in, let's see, mode, in radians, I want to see if it gives you the decimal. It probably will. I forget offhand. Let me just double check. Do the same thing, all right? Second cosine, negative 1, close this, enter, gives you pi, all right? It gives you the decimal. It doesn't give you the symbol, all right? You know what pi is, 3.14159. This is to 10 degrees, 10 decimal places of precision, but you recognize pi. I bet money on that. All right. Anyhow, just know that if you start in degree mode, you'll get something maybe a little bit more comfortable. All right. It's a little less familiar when you get some fraction of pi, right? Because it's an irrational number to begin with, so it has a lot of decimal places, and it's not going to necessarily be 3.14, right? It will be, half of that, 1.57, whatever, In this case, that's what it is. All right. Yes, use your calculator to validate. All right. But be able to recognize and utilize this diagram. Okay. Now, there is no second answer to this as in the first example, because in the interval of 0 to 2 pi, that is the only instance where the function of cosine is actually negative 1. Right? So you don't have to worry about a second thing. All right, let's do another. In this case, we'll do a sine. Try to do it a little bit more cleanly. 2 sine squared of theta minus 1 equals 0 in this case. Again, I'm making this red because I'm trying to emphasize that that is the actual objective here, what the value of this is. That's the variable. All right. So that means that we have to move everything around it ultimately. So as before, drew a little table here. move the parts around. So start with the addition and subtraction. Right? Justify moving -1 by adding 1 to both sides. There's a cancellation effect. Right? That means that this 2 sine squared of the angle is equal to the outcome of 0 plus 1 is just 1. Right? Positive is superfluous, but hey, sometimes helps when you're drawing a picture. Okay, that might be my done today. Next thing is, I'm sorry, I'm muttering to myself. My markers keep drying out, so and I go through I have a little cup here of markers. And I'm like, which one is the bad one? Well, I think my red is fading out and my other black too. Anyhow, move this 2. How so? This is, again, pressed together. I'm just emphasizing with a dot here. This is being multiplied to start, so if I want to move 2 from here to here, over equals, do the opposite. The opposite of multiplying is dividing. If I divide by 2 here, I'm obligated to divide by 2 here. There is a cancellation effect. And that means that this is the sine squared of the angle is equal to positive 1 over 2, so 1/2. Right. Still not finished because we have an issue here, right? Different from the last problem. We had actual cosine before, not squared cosine. And in this case, we have a sine function, but it is squared. So we're going to perform opposite operations as traditionally, right? To justify getting rid of this. What is the opposite of squaring something? Indeed, to square root, right? And then, if you've done it here, you have to remember you're obligated to do it here. I'm going to erase this now just because I don't want to conflate it with anything else. There's going to be a cancellation effect by design on this side. This will cancel this, all right? Which means that you would be left with what the guts, the radicand, right? Underneath the symbol, the radical symbol. And you'd have still the sign of the angle, right? In this instance, you have to be conscientious, again, because this is comes from a trig function, so it's periodic, right? And although I didn't specify, let me do that now as a dodo. We're still looking for solutions in this interval, more or less the normal case. Between and including 0 and up to 2 pi, not including 2 pi. That's just the way you stop, right? So more or less the normal period of, in this case, the sine is normally 0 to 2 pi anyhow. Right? We have to bear in mind when you take a square root that there's a positive possibility here and there's a negative possibility. So I'm going to sort of write this on the outside of the radical symbol. Okay. And this is what we're left with. Plus or minus 1 over 2. All right. There's a couple of tricks we're going to pull at this point. All right. We're going to try to factor this. All right. We're going to take advantage of the quotient rule for radicals, which says you could separate out the parts. Right. You can separate the numerator from the denominator as long as you keep both of them inside of a radical. Perhaps one of them is a perfect square. In this case, the very top will be. Right? And we'll see what we get. I do need to erase this, unfortunately, but I'll leave that at the bottom. Right. Couple of things. If this is what we're working with, I'm just duplicating this to get it off the floor here. And we then apply the quotient rule for radicals, which which is to say, okay, you could make this the square root of 1 independently of this, the square root of 2. All right. Then what you would have is this, next step. You'd have the sine of the angle is equal to, forgive me for this, I'm trying to be consistent here. The square root of 1 over the square root of 2. What is the square root of 1? Right, by itself. It is a perfect square, the number 1. So that at least will escape the radical. But the square root of 2 is famously an irrational number, like pi, so you're stuck with it. The thing is, now we're getting in trouble because we're coming into conflict with etiquette. All right, we live in a world where there are calculators, so it really shouldn't matter, but we still conform to this etiquette, right? Right. It really, in a world without calculators, would be to our benefit to do this. Right? Rationalize the denominator. At least eventually. The only thing that I would do before I dress this up a little bit further, which really is just going to amount to moving the radical symbol around so that it is not a denominator. Right? No no radical in a denominator is what happens when you rationalize. I would take into consideration what these dimensions are in respect of sine. All right. What I'm getting at is preserve this much information. I'm going to write it again a little bit more cleanly. Right. This is my dud. That's the dud. Okay. The sine of the angle is really 1 sitting on top of the square root of 2. Save this information before you do this. Because, all right, we need to at the same time remember what is sine. Sine is opposite, according to SOHCAHTOA, and this is a hypotenuse. All right. In respect of a unit circle, that makes opposite a y dimension, and it makes the hypotenuse an r dimension. All right, so we're going to draw a picture, all right, and we're going to take advantage of special right triangles because these relationships here come from one of those. I'm running out of space, so I'm going to move some of this. I'll erase that finally. A couple of things. Here are still our special right triangles. That are good to know by heart. The triangles must have a 90-degree angle. That is their key feature. The type that is oriented like this, 30 and 60, the 30, 60, 90 triangle. Again, along the edge of the 30 is the square root of 3. Along the edge, whatever the orientation of 60 is 1. And the hypotenuse is 2, right? For that type of a right triangle. For the alternate type, the 45, 45 type, the dimensions are 1, 1, and the square root of 2. If this is the situation that we're ending up with, right, where we have a y value that is 1 and apparently a square root of 2, of these two choices, obviously, which one are we going to look at? the one that has the square root of 2 in it, right? If there was a square root of 3 here somehow, it would be more appropriate if it was a top, all right? I would look over at the 30, 60, 90 instead. But if I see this telltale sign here of square root of 2, we're probably dealing with this situation, right? The only downside to it is that we have a second condition that we have to consider, which is that this is, again, on a circle. So I'm going to erase some of this. And use my little stencil here. And I'll take this triangle that we know we're dealing with because of that telltale sign, square root of 2. Yes, I'm still going to get to rationalizing, but not yet. All right. And draw this triangle into it. Okay. Now, where to put it? Should I put it in the first quadrant, the second quadrant, the third, or the fourth, or more than one? All right. In theory, one whole circle would be in that interval of 0 to 2 pi. Because it came from square roots and there is this potential combination, all right, we got to be careful. It's probably going to be 2 answers, right? So let's dissect this a little bit further, all right? I'm going to remind you again, all right? It is x or y only that is negative. Well, that is potentially negative. Never the r value. The radius is never going to be part of this. Right? So in the instance of positive 1 over the square root of 2, right? That means positive y. Right? And in the instance of negative 1 over the square root of 2, right? That means negative y. Right. These right triangles have to be drawn perpendicular to the x-axis. Right? You're never going to draw a triangle like this, ever. Never do that. Right. Where are the locations of positive y? Right. Let's see. This is a positive y. And this potentially is a positive y. These are both positive y's. Right? The x's are really irrelevant in this case. This would, in fact, be a positive x, right, along this dimension if it mattered. It doesn't really matter, but this is a negative x in this case. Simultaneously, there's this possibility in the same interval. The negative y's, we've just considered this. Let's consider the negative y's. Where are the negative y's? That's negative y. And this is potentially negative y. Looks like some kind of weird sort of a math club symbol. Join my cult. Let's see. All right, so in this case, actually, we're not just going to get 2 answers, we're going to get 4 answers for this, all right? Because they didn't specify what the x's are going to be, we can't really say that it has to be limited to 1 and 4, all right? We're going to basically have to consider all 4 possibilities, Right. Here is the R here. Here is the R here. Here is the R here. And here is the R here. Okay. Let's start with the most basic incarnation of this. All right. In standard position, all right, would have us a 45-degree angle here. Okay. Then in theory, a 45-degree angle here. Just realize that in order to calculate that, it's reading backwards from 180 rather than reading forwards from 0. And this would be, in other words, subtracting from 180, and this one would be adding to 180, and this would be subtracting from 360. Okay. I should fill in the dimensions as well. They'd be 1s. Opposite of 45 here is positive 1. Opposite of 45 here is positive 1. Opposite of 45 here would be negative 1. And opposite of 45 this way would be negative 1. Okay. The R values in each case would have to be the square root of 2, the square root of 2, the square root of 2, and the square root of 2. Again, the R values are never negative. The radii are never negative. It's only the x's and the y's that can be the negative. All right. Spares you from having to worry about it. Okay. So, let's figure out what the equivalent degrees would be. All right, and then translate that into pi radians. All right, I'll do this rationalizing thing as an afterthought. It really isn't that important, but a lot of times what happens is you don't end up with something helpful. You end up with the rationalized version of this. And the only reason I would bother you with the exercise of going forward with that, which converting this, it would be taking this denominator and multiplying by a convenient ratio of 1. So if you saw square root, a convenient ratio of 1. If you see square root of 2 as your denominator, you'd see the square root of 2 sitting on a square root of 2. Right? They're irrational, they're ugly, but it's something divided by itself. It's still 1. It's still multiplying by 1. It's not changing the value of this. It's just changing its appearance for the sake of etiquette, really, at this point. So it would be square root of 2 sitting on top of the square root of 2 times the square root of 2 is the square root of 2 squared, right? Or the square root of 4 is the equivalent, which is just 2. You might see this in your book, right? For what's sitting here, right? Rather than what would actually be more practical when you're trying to draw a picture to decide what the angles are, right? So just beware of that. This is the rationalized incarnation of what you have to work with here. In black is better, right? In blue is just what is possible to rearrange the parts. Anyhow, now that that is out of the way, right? Let me free up some space here. And we'll figure out what the angle is. Right. As I mentioned, if you wanted to with your calculator, as the dud, you could at this point, when you've gotten it to 1 over the square root of 2, you could take your calculator's inverse function of 1 over the square root of 2 and then let it tell you what the angle is, right? If it's positive, it's probably going to spit out the angle that is the first angle, which is this one oriented here. So 45 degrees, right? If you tried a negative one of these, I don't know if it will work. Sometimes it won't. If you get an error message, it probably has to do with the fact that it would be outside the spectrum that is allowed for an inverse function. Remember, inverse functions have to be 1-to-1, right? So they have to pass the horizontal line test, which means that they're chopped down quite a lot to maintain status as a function. Here, watch what would happen. If I put in inverse sine of 45, all right, it should just spit out the decimal equivalent. Oh, wait a minute, sorry. The inverse of 1 over the square root of 2. This should give you, since it's in degree mode, 45 degrees. Did I change the mode? Yeah, I think I did. Yes, I left it in radians when I shouldn't have. So, putting it back in degrees. That is apparently what 45 degrees is in radians. That is, if you took 3.14, which is pi, and chopped it up into fourths. All right. 3.14 divided by 4. A quarter of pi, yeah. I'm sidetracking here when I shouldn't, but that decimal of 0.785 is not pi. It's not pi radians. It's regular full-blown radians. It's really the equivalent of what you would get if you took 3.14159 and divided by 4. See? All right. Anyhow, since it is now in degree mode, all right, I'm going to type this ratio of 1 over the square root of 2. It's easier to do it while looking at it as opposed to a reflection. Okay, so entered like that. The inverse of the ratio will spit out the angle, 45. All right, what is it in pi radians? Pi over 4, 45 degrees. Again, the problem with this is that it's only telling you the first one out of the potential 4 of them. So you need to draw a picture in order to infer or reason through what the other ones would be. Okay, if in theory, all right, you typed in -1 over, no, I don't want that, the square root of 2. Let's see what happens. You might get an error message. I forget offhand, but here it is, the negative possibility. And again, it would only tell you maybe the second one out of 4 of them. It gives you -45, okay. Would be that one, all right? All right, it's not telling you this one and this one. It's just giving you potentially these two. All right, so if you're trying to figure out what the angle is to this one, all right, it would be backtracking from 180. So this one, which I'll put in a different color, is 180 minus 45, which should be what, 135, I believe? Okay. Double check. 7, yep, yeah, 135. All right. Good. Okay. Then there's this one, which I'll put in green. All right. I'll put this right. Yeah, that's nice. Okay. This one that's down here, this angle that goes from the axis to 45 terminal, -1 for y, is 180 plus an additional 45. All right, which in this case would be what, 225? All right. 225 degrees. All right, and then one more. I wish I had another color. I'll put it in black. Yeah. This one, which is negative 45, at least your calculator can tell you that, is subtracting 45 from 360. Which would be what? Let's see, 325? Let's see, 40 would be 320, 315 rather, okay. 315 degrees, okay. Now, in each one of these cases, although these are all legitimate answers, right, that's the answer for what the angle could be, right, in this interval, right? That's the answer, and so is this, and so is this. Most likely, if you're looking at the solutions in your back of your book, or if you're doing anything online, they're probably in pi radians. So you would have to convert each one of these to pi radians. Move that. Okay. Or use your reference. 45 times pi over 180 is 45 pi over 180. Both of them are divisible by 5, but the actual best choice would be 45 itself. 45 times 4 is actually 180. So this is pi over 4. That's pi over 4, right, for the angle in pi radians. 135 times pi over 180 is another alternative, top times pi. 135 over pi times 180, all right. Again, the GCF in both of these cases, I can tell you from experience, will be 45 itself, all right. So this is going to be, I believe it is, let me just double check. 25, 225. That's that one, all right. I'll get to that one, sorry, went too far. 45 times 3, 15, yep, there we go. This is 3/4 pi, all right. The one that I kind of just jumped the gun, 225 times pi over 180. Make a space here. $225 over pi over 180. Again, the GCF should be 45. So this is going to be 4 again. 225 is what 45 times 5 would be. 20, yep. So it's 5 pi over 4. That's this one. And then 315. 315 pi over 180. This is going to be 4 something pi. 45 times, let's say, it's 7, is it? I believe it's 7. 35, carry the 3. 28 plus 3 is 31. Yep. 7 pi over 4. Okay. Again, being able to convert using conversion factors like that is a skill that don't throw away. It's invaluable. All right, but you could use your references again. So not to beat a dead horse, but I'm going to point at this once again. If you've identified that the angle you're working with is 45 degrees, in terms of pi radians, it's pi over 4. Now look at where all the reds are. All right, 225, 5 pi over 4. 315, 7 pi over 4. 135, 3/4 of pi. All right, it's very handy. All right, it's also something that would be good to memorize in the long run if you're inclined to. All right, let's see. that's the intricate details of that. Let me speed it up a bit. All right. Again, just to reiterate, use your calculator to validate. All right, it's a great thing, especially since you paid for it, right? Super duper. All right, but just realize it's limited in what it can tell you in terms of the answers. At best, it can only tell you these two solutions rather than all four of them. All right, so that kind of stinks. All right, be able to draw a picture. All right. Here's another possibility. On time, good. Here. All right, suppose you get something that is not one of the main three trig functions, sine, cosine, or tangent. Let's say that you get stuck with something like cosecant of the angle, right? And it equals -2. And as a side note, they say, well, you gotta fit it in this interval, 4 pi. Right, so there's going to be multiple solutions potentially for this as well. Just don't be intimidated, all right? What you're going to do is you're going to translate this into sine, cosine, or tangent first, all right? And if you happen to have the handout from most recently, which is this type, all right? And you look over at your reciprocal identities, and remember that sine and cosine are reciprocals, right? So if cosecant is, pardon me, that sine and cosecant are reciprocals. If you see that cosecant is a denominator in the identity, all right? Switch the position of these two, and there it is a somewhat of a numerator, all right? What I'm getting at is that you could rewrite the problem, right? And I really should put the angle in there. This is the same as starting out like that. Because cosecant is the reciprocal of sine, and it could be said conversely that sine is the reciprocal of cosecant. If it's oriented like as a numerator to begin with, then its reciprocal would be its denominator, like so. Okay. Then you're still going to pull tricks. You're going to do what you normally do when you're solving an algebraic equation, which is move the parts around. All right. How so? By opposite operations. Do opposite operations. All right. Again, do to both sides of equals. So, if it is understood that this means division, I want to get this to a more ideal state where it is not a denominator, it is a numerator. The opposite of dividing by sign would be to multiply by sign. And if I've done it here, in order to legally get away with it, I must do it here as well. There is intentionally a cancellation effect. So what does that leave me with? It leaves me with a 1 behind. And then on this side, it is -2 times the sine of the angle. You've noticed that I've dropped putting parentheses around things sometimes. That's just being sloppy, all right? So not having that doesn't change it. It just means that I neglected to do what would have been nicer, better etiquette, all right? Anyhow, I like to draw my little Easter eggs here, the theta. And now just move the 2. The opposite of multiplying by -2 is to divide by -2. And if you divide by -2 here, you're obligated to do it to the opposite side. negatives cancel, 2's cancel just sign. This is the end result. Cosecant of the angle is really this written more nicely. I'll put it in red. Okay. It is sine of the angle is equal to negative 1/2. Now incidentally, I know that this thing started out as a negative 2, and then I moved it down here, so in theory it's a denominator. Just realize that when you're trying to basically decide what the fraction's sign is overall, right, in a textbook it would probably be not favoring either one of these, all right? What I would be kind of obligated to do is make sure that that sign is attached to the top. That is what the equivalent would be in terms of integer arithmetic, all right? Reason that I'm making an issue out of it is because remember that this is going to be a hypotenuse ultimately. So it has to be the positive of these two things. So whatever sign's ratio is, whether it's an x on top or a y on top, and it should be a y, all right, just make sure this is the thing that's negative, not the hypotenuse. Okay, now at this point, we're going to see which triangle of the two special right triangles this correlates to. The 30, the 60, 90, or the 45, 45, 90. And then draw those right triangles superimposed onto a coordinate plane inscribed in a unit circle. All right, let's see. Inscribed in a circle. All right, I gotta put this over here because I need the space. Negative 1 over 2. A couple of things to remind you. Sine is opposite over hypotenuse, which is the same in this case as saying y, right? At least in the beginning, over r. Opposite of whatever the angle is, right? At least if it's in standard position. All right. To start with, so let me get to that. Let me draw two special right triangles for reference. All right. This is our information. $30, $60, $90, square root of 3, 1, 2. $45, $45, $90. 1, 1, square root of 2. Alright. This involves regular 2 as opposed to the square root of 2. So of these two special right triangles, this is the one that is relevant. Okay. And now, behold the special effects. I'm going to draw a nice a circle in here. That's somewhat nice. And try to make this nice. We're going to start, since we're in the interval of 0 to 4 pi, right? Here's where 0 would be. Here's pi over 2. Here's pi. Here's 3 pi over 2. Here's 2 pi. If it's 4 pi, this is going to be 2 complete rotations. Okay. That we would have solutions. And I'm going to draw my right triangle now. Okay. Let's see. Now, where to put this if this is a negative on top, right, and again, it's only the x or the y value that could be negative. In this case, since we're talking about sine, it's a negative y. Let's draw a right triangle exclusively where there are negatives that are y's. Exclusively. Alright. Here's quadrant 1, here's quadrant 2, here's quadrant 3, here's quadrant 4. Alright. The location of negative y's would only be in quadrant 3 and in quadrant 4 respectively. Include that information. Center. This is negative y. This is negative y. And here's r. And here's the other r. If this is negative 1 specifically, right? Then this is 2. And if this is negative 1, then this is 2. Okay. In theory, this would be the square root of 3 from here to here. And this would be the square root of negative square root of 3 from here to here, because it would be a negative x. Okay, next thing. Let's figure out what the angles would be. Borrowing from the special right triangle, right? Opposite of 30 would be 1. So the angle that would be here, since it would be opposite, would appropriately be a 30-degree angle rather than a 60, right? Same thing here, right? The opposite of this angle would be negative 1, so it would be the 30 rather than the 60. All right. That means that we have these two angles to start with. We have the 1, and we could basically, again, use your calculator for this much information to arrive at least the first one, or at least one of them, perhaps. All right, but we have, let's do this one from here to here. All right, that angle would be 180, because that's pi, plus an additional 30 degrees, all right, which would be what? 210. Okay. If you were to go backwards from here to there, all right, that would be 360 minus 30 degrees. All right, you could, if you wanted to, figure out what the balance would be. If you know that this is 270, you could add 60. All right? But this is probably the easiest thing, subtracting from 360. So this would be 330 degrees. Okay. Now, here's the problem. There's going to be rotating this through 2 complete cycles. So we're going to get another one that is coterminal to 210 and another one that is coterminal to 330, right? And the way that we would figure out what that is go through, from this point, add another complete 360, all right? So whatever 210 is, add 360 to go from here, and then through one other complete cycle is 360. And then this one, 330 plus 360. All right, which would be what? 570 degrees. And this one, 690. Just to make sure that I'm not exceeding the maximum. And the maximum would be 4 pi. All right, 4 pi would be 180 times 4. So perhaps I'm stretching a little bit beyond that. I gotta make sure. Let's see. 0, 32, carry the 3. 720 is the maximum. This should just fit, all right? 690 is just shy of 720. Well, not just shy, but it's under it, all right? So we're not exceeding it, all right? That's, again, we figured out that this is really 220. One extra cycle through here, all right, is in the realm of 4 pi. Then there's this one, which we figure out is 330, all right? One extra cycle through there, all right, is adding 360 to that, so 690. Okay. All right, now, unfortunately, each one of these has got to be converted. 210, 330, 570, 690, 2 pi radians, all right? At least that's what the choices in the back of a textbook are potentially in. So, we'll do that. Let's see. I want to just verify. You could get your calculator to give you this much information. All right, if you type in the inverse function. All right, the inverse sine of -1/2 would look like this. And you see that it gives you -30. -30 is it's giving you that one specifically. Okay? Not unfortunately the other conditions specified here. Let's see. So, 210, well, I'm going to cheat, at least for the first couple of them. Here again is that diagram. A little bit larger, so perhaps it's easier to see. Okay. Here's 210, 7 pi over 6, all right. Here is 330, all right, which is 11 pi over 6. And 330 is this one, 11 pi over 6. Okay. If you added 2 pi to this, you would get the equivalent of 570 and 690. Let's see. This should be 7 pi over 6 plus 2 pi. That's like 12 over 6. 2 pi is the equivalent of, well, 2 is the equivalent of 12 divided by 6, right? I'm just using the same denominator. 12 over 6, add 7 to 12, you would have 19 pi over 6. 7 pi over 6 for 212 in the 2 pi frame. 19 pi over 6 for in the 4 pi frame. Right. 11 pi over 6 for 330. Right. 11 pi over 6 plus 12 again over 6. 11 plus 12 is what? 23? Yes. 23 pi over 6. Again, I'm cheating a little bit because I'm using a reference to establish these two, right? But you could brute force do what we had done before. Take 210, divide by 180, all right? You're gonna get 7 over 6. All right, here's proof of that. Right? If you use your calculator to do fractions, all right? Let's just change the mode. Again, this is assuming the software is up to date. If you hit alpha and then F1, you can go right to this menu, the intuitive numerator over denominator. Type in 210 sitting on top of 180 because that's what the conversion factor would result in. and then there would be a pi next to it. You'd have to infer that. 7/6. Okay. Similarly, if you typed if you typed 570 over 180, 11, what is that, 19/6, 19 pi over 6. You have to, as an afterthought, go, oh, well, it's a fraction of pi, though. Okay, that goes up the conversion factor. Similarly, 23. Okay, more than one way to go about it. Backward here. Alright, so 7 pi over 6, 11 pi over 6, 19 pi over 6, and 23 pi over 6. All feasible. Alright. Let's see. We'll do maybe 2 or 3 more of these and then I'll stop. I'm just trying to cover all bases. Okay. Let's say you had one involving tangent. And they kind of give it to you screwed up, as they often do. There's a lot of things that if you trust yourself, and I think that's the hardest thing for American students in general, is that we don't assume that we're capable of doing something. We're kind of conditioned to go, oh, it's only the special people. No, it's not true, right? You see me make mistakes all the time, right? But I catch myself. Why? Because I write my thoughts, all right? I trust my own ability to figure something out. And if there's anything I can impart to anyone, I want you to realize that. I'm not special, you know. Anyone can do this, right? Motivation is everything. Right. So, let's say that you had this situation. You got to solve, and you have the tangent, and the argument here is kind of messed up. Is equal to 1, and they tell you these specific conditions, and you want your solutions in this frame, 2 pi, right? Now bear in mind a couple of things. A graph of tangent, I'm just going to draw it just for reference, right? Here's a graph of tangent of theta. We had a couple of classes ago, had this established. Tangent is a curve that looks like this. I gave you 3 increments this way, and 3 increments this way, well, 4 total. But the one that is really useful, right, in this case, aside from where the asymptotes are, negative pi over 2, which is negative 90 from 0, and pi over 2 is positive 90 from 0, man, I'm really hunching, is pi over 4, the 45-degree angle, and negative pi over 4, right? That's the second of the, like I had calculated for pi over 3 and for pi over 6, right? So basically, I had when we were doing the graphs, I said, all right, let's try to figure out what the coordinates would be if you used 30, 45, and 60 degrees, respectively. And that's 90 is the extreme, the asymptotes. The one that is the 45, which translates to pi over 4, that's the one that gives you 1, right? So I would argue that's probably the most important in terms of the picture. And also the origin. Anyhow, you get a curve that looks like this, the tangent. And it is a wave because it actually repeats. There'd be a similar looking shape this way and this way, right? The boundaries of tangent are negative 90 and positive 90 if you wanted to use degrees instead, right? But this pi over 4 and this negative pi over 4 are going to be helpful, right? If you typed in the tangent of 45 degrees, which is what pi over 4 would be, you'd see it's going to produce positive 1, right? if you typed in the tangent of negative 45 degrees, all right, you're going to see it gives you -1, all right? That's what this dot would be as part of the curve. This is where the curve would exist here, all right? Anyhow, the normal spectrum in which we talk, the period in which it takes to complete the wave, the complete tangent, all right, is how wide normally. This is a bad drawing, but what's the period? It stretches from -π/2 to +π/2. How much is that in terms of pi in general? The period for tangent is just pi. That's how far a distance it is from here to here. All right, a half and a half is one whole. All right, whereas sine and cosine takes 2 pi. Now look at the weird conditions that you're being given in this problem. They're saying, hey, I want you to give me all answers in a non-verbal way. That's what this is saying. Give me all the possibilities, all right, beyond its normal boundary, all right? Now if I should complete this one, here's the inside guts of this. Let's infer a couple of things. All right. Having a picture like this for reference is going to be helpful when you're trying to figure out a problem like this, because look what the result should be. The result of this tangent function on some angle, whatever it amounts to be, is going to be 1, all right? This is normally this. The tangent of 45 degrees is what is 1. So if you think about it this way, and I'll put this in red to emphasize. Pi/4, and this is 0, or theta minus pi/2, right? This is behaving similar to, I mean, they didn't call it this, but it's like a 1-to-1 relationship. If you translate the amount of 1 into something that would be pi onto the normal conditions, the angle of 45 degrees, which is what this is, that's +1, all right? All right. Then what you could do is you could calculate this slightly modified version of the equation. If it's tangent on this side and it's tangent on that side, the only thing that you really need to pay attention to are the guts here, the arguments, all right? What this equates to and what is actually written in the problem here. Pi minus a half pi. It's basically behaving as something that is 1-to-1, all right? When we were talking about logarithmic and exponential equations, a technique for solving an exponential equation or a logarithmic equation potentially was when it was 1-to-1, when there was the bases on opposite sides matched, and the only thing that you really had to pay attention to were the exponents, and they became kind of their own little equation. Similarly, if the log was the same type of log, like log 10 on one side and log 10 on the opposite side, you could just pay attention to the guts, the arguments, right? And this is a much simpler equation. Right. So, what's the opposite of subtracting pi/2 if I want to just move it? Add pi/2, add pi/2. There's a cancellation effect by design. That means that theta, at least in one instance, is the sum of pi/4 over pi/2. I'm trying to give it its little hat there. All right. This is the same as a half, and this is the same as a quarter. All right. What's a half plus a quarter? 3/4. All right. If you have to, you could always upgrade it to a common denominator. It would be, if it's a 2 down here, it would be 2/4 as an equivalent, as opposed to 1/2. 1/2 is 2/4. And this is 1/4. That's just putting a 1 on top to make it obvious. 1 plus 2 is 3 pi/4. Right. whatever that angle is. If I remember correctly, what is it? It's like 135 degrees, right? Yeah, let's do it real quick. 3 times 180 divided by 4 is 135, it is. Okay. Now, that is 135 degrees. And you may need to sort of, in your mind, toggle, that's annoying, I know, back and forth between radians, pi radians, and degrees. How come? Because you might be a little bit more comfortable, even if though it's an arbitrary increment, degrees, going, okay, that's outside, that's still within this realm, all right? Is it possible, all right, to get something that is equivalent to this, all right, that is just shy of 360 degrees, all right? The equivalent of 3 pi over 4, all right? It is, all right? And in that case, all right, we're going to add the period, all right, and see if the period is still underneath, all right, 360. We're going to add the period of tangent, which happens to be pi, that's how long it takes to complete, right? To see if there is another solution under 2 pi, that is under 360 degrees, right? If you added 2 pi to 3 pi over 4, you'll get whatever that equivalent is in terms of pi. I'll do it both ways. Or if you know what the angle is, right? And you added 180 to it. Let's see if that's under 360. I'm sorry for the mess. 11, 315. Yeah, it fits. All right. You could squeeze one more out of this. All right. All right. It will repeat. All right. So 315 degrees. All right. I'll put it up here. All right. For our collection of solutions. All right. What is theta? Theta, in order to produce this result, all right, is going to be 3 pi over 4, which is the equivalent of saying 135 degrees. All right. Another possibility fitting in this spectrum of what is allowed for answers, right, is apparently 315, which in terms of pi radians, right, it's the equivalent of doing 3 pi over 4 plus an additional 4 pi over 4. The reason I'm doing 4 pi over 4 is that's what pi is in the style of that denominator. Right. So what is that? 7 pi over 4. If you converted 315 degrees into pi radians, it should be 7 pi over 4. Right? Another way again to cheat is to look at your reference. Right? If you're not going to use conversion factors. Right? So again, I'm really trying to stress the usage of this. All right. Let's look at 135. Here's 135, 3/4 of pi, and here's 315, right? 7/4 of pi. Both of these would produce, in terms of tangent, all right, if you plug that angle into here, you're going to get 1 as the answer. Okay. That is, you took these angles, 3/4 of pi and 7/4 of pi, put it in here in the original argument, subtract out 90, then took the tangent of the angle, you would get 1. It's a lot of intricacy, right? Sometimes it's knowing even what to ignore temporarily while you're doing your calculations. That's not very concise. I mean, what I'm trying to say is that sometimes when you're doing a calculation, you cannot allow yourself to be bogged down by certain details. You just have to just temporarily say, all right, I'm going to accept what logic is being given to me, all right, and follow it through to the end. And if you hit a brick wall at that point, then you go, maybe this was something wrong to begin with. And you could backtrack, all right? Anyhow, this is correct. All right, it's 3/4 pi and 7/4 pi. Pardon me. 3/4 pi and 7/4 pi, right? 7, 5, and 4, same difference. Okay. Only on time, a little over, okay. I don't mind doing a lot of these because I think the more that you do, the more clear something becomes. You get more comfortable with it. That's true of everything in life. You get a lot of experience, then you're not intimidated. Bear with me 1 second, I gotta just check something real quick. Okay. All right, let's see, moving on. All right, here's one that's a little bit more algebra-y, if that's the name of the word. Like algebra, we'll cease to use the theta, and we'll use x variable. More solutions. So if you have, let's see, 2 times the quantity, the tangent of x, plus 3, this is isolated in parentheses, it's faint. That's kind of leaving a reflection, so I'll leave it off. All right, is equal to 5 plus the tangent of x, and in this interval, between 0 and 2 pi again. All right. If you're given a variable x, here, and I'll emphasize this like so. We're going to solve x. It is an angle because look where it's attached. It's attached to a trig function, so ultimately you're going to get an angle. You can convince yourself, if you're getting an argument like that, right, you're going to get an angle for an answer, whether it's an x or it's a theta. Right? But apply the rules of algebra as you would. Right? If you can't combine these two things, before I start moving things over equals, which is actual algebraic technique, let me just try to tidy up this side, which is more or less applying rules of arithmetic. All right? If there's a 2 sitting on the outside here, then the most that I can do is distribute 2 to each of the contents. Right? At least that will expose it to the open air. That means that you would have 2 tangent of x, right, plus 6 is equal to this unchanged tangent of x plus 5. All right. Let's try to isolate the trig functions to one side and isolate the regular ordinary numbers to one side. Since this is what includes the variable, I'm probably going to shift this over to here. So, big table. Make this a little bit more obvious. This is an equals here. And move the guts. Okay. Pull 6 over here by subtraction. There's a cancellation effect. All right. And you would get -1 as a result of that. All right. If simultaneously I wanted to justify moving tangent over to the opposite side, there's my dud. For green, I'm going to do the opposite of adding here. The opposite of adding is subtracting tangent. There's a cancellation effect again by design. All right, and I'm going to strategically park it underneath the thing that it most closely resembles, which is tangent here. Now, if there is no coefficient, assume it is 1. Okay, and then combine the 2. 2 minus 1 is just 1, which means that you really don't even have to put 1 tangent of x here. You could if you want to. I would just simply reduce it to its most concise form, which is this, the tangent of x. Right, and it happens to be a negative. Now remember, we do have to bring up a couple of things. First of all, put this in a little thought cloud here. What ratio does the tangent of an angle represent? Opposite over adjacent, if you're using SOHCAHTOA. If you are translating that into x's and y's, right, it's a y value over an x value. Notice that there is no r involved, right? Which means that that opens up a lot of possibility. All right. Remember what I was saying before. It's either the x's or the y's that are negative potentially. It's never the r value. All right. But there is no r value involved in this. So which means that if you just have the whole number of 1, you have a lot of choices, right? What is 1? Perhaps it would be more obvious if I did in fact move this 1, right, over to here. That is one possible combination, all right? A second possible combination would be this, where I make the negative the denominator instead, all right? That is to say that instead of it being a y, that's the negative, I can make the x the negative, all right? And that means that if you drew a picture, and we're going to have to now, all right, and that's going to give me a couple of different angles, right? Because of these two possibilities. The integers, oh damn integers. All right. All right, so this is really what we're looking for, all right? I don't want to erase too much. We want to know, I'm going to draw it under here. We want to know what the angle is, and it's unfortunate that it's an x really. Beta would have been better. All right, just not to confuse it with the dimensions, all right? We want to know what this angle is, all right, given this possibility to this possibility. So let me draw a picture on a coordinate plane. I have to clean this bed better later. All right, here is again a circle. Stop shifting. And here we are again confronted with where to put the right triangle. Quadrant 1, quadrant 2, quadrant 3, or quadrant 4. Here's 0, here's pi over 2, here's pi, here's 3 pi over 2, and 0 is also the location of 2 pi. So one complete cycle. And here's dead center. All right. If I'm going with the situation of -1 being broken up into a -y over a positive x, all right, then where's the location of -1, negative y? Negative y's are in the third quadrant and the fourth quadrant respectively. That's a negative y, that's a negative y. All right. And again, remember, you're always drawing triangles oriented like so. The y dimension is perpendicular to the x-axis. So you have that. Okay. Then there's this situation. Where you have a positive y over a negative x. I'll put that in green. Where is positive y located? This is positive y, and this is positive y. Another one of these funky drawings. In the case of positive y, we would have a negative x. Let's see. That will limit some of our choices now that I'm taking that into consideration, which is great. All right. If this in the green here is this situation here, where you have a positive y and a negative x, that's fine. All right. That would make a -1 value overall. All right. However, all right, this shares a side with this situation where you have a negative x and a negative y simultaneously, which means at this point I can eliminate this as a possibility, right? Because I can't have both a negative x and a negative y simultaneously, all right? This other negative y is perfectly fine, all right? This side here would be a positive x, and if I consider these two dimensions in tandem, positive x and negative y would be this situation, all right? But, all right, it shares a side with this potential positive y. And in this case, as over here, all right, I can eliminate this as a possibility, because if you have both positive dimensions, you're not going to get a negative. So I can now, at this moment, eliminate this as a possibility. And that means that there's really only two solutions here. The angle that starts from 0 and goes to here, all right, and the angle that in theory starts from 0 and goes to there. All right. Now, as for what the actual angles are, I do have to reconsider my special right triangles again. All right. If I have the 30, 60, 90, then it would be square root of 3, 1, and 2. And if I have the 45, 45, 90, that would be 1, 1, and the square root of 2 in standard position. That means that this would be running along 0 degrees here, along the x-axis at 0 degrees. All right. I'll have to modify it slightly. All right. But if the dimensions involved here, if the ratio is 1, what situation am I really going to end up with? If it's an x and a y, and the overall, the outcome, the quotient of y's and x's has to be 1, then these are what the parts would have to be, right? 1 over 1. Same thing here, right? 1 over 1. So it's going to be this triangle, not that one, okay? That means that you're working ultimately with a reference of 45 degrees. Right? There would be a 45-degree angle tucked in here to represent this triangle. All right. However, what does that mean in terms of the bigger picture? All right. what's 180 minus 45? The first angle, that's this triangle here. Sorry for the sloppiness. I'll erase this unnecessary stuff here. And this unnecessary stuff here. If you're backtracking from 180, because that's what pi is, 45 degrees, then the angle in respect of 0, all right, would be whatever 180 minus 45 is, which we had calculated before is 135 degrees. Okay. Now, in this case, you could do it one of two ways, really, right? You could figure out what it is. 80 down here would be 270, and then the balance from 270 to 360 would be 90, and half of that would be exactly 45. All right. In other words, you would add 45 to 270, or probably more efficiently, you would just say, well, I'm going to go backwards. Right from here. And I'll just go 360 minus 45. In which case, instead of 135 degrees, the other potential angle would be 315. All right. And again, that's what it is in degrees. And that's really what the angle is that we were looking for. They just happen to call the angle x's in this case, which I wish they wouldn't. What is this in radians? All right, we had probably done these calculations already, but again, use the reference. All right, and we'll see. Here's the reference. Here's 135, 3/4 of pi. Here's 315, 7 pi over 4. 7/4 of pi. So that's what this is, all right? 3 pi over 4 and 7 pi over 4. All right, and that fits in the realm of 2 pi, of course. All right, so it's only 2 solutions. All right. Let me do something that's quadratic. And in that case, I'm going to get back to this older reference. All right. We're going to have trig functions, but we're going to have something that it simulates an algebraic equation that's quadratic. So this is the reference for solving quadratic equations, and it's factoring and the zero product rule 9 times out of 10. Alternatively, it's using the quadratic formula. So either this method or this method for something that behaves quadratic. That is, if you see an exponent of 2 attached to the trig function. Right. So, my books are falling apart. Okay. Right. This will be second to last, right? That's why. Again, I'd rather cover all bases, right? You could ignore certain parts of the video if you feel comfortable with the material, but I don't feel bad about, making it long, except that it just takes forever to upload. Right? Anyhow, better to be thorough, right? I think so. At this point, I might just do that. Here we have this. All right, suppose this is one that you'll have to use the quadratic formula, sadly. Something that behaves as quadratic. So if you had the cosine squared of theta plus 3 cosine of theta minus 1 is equal to 0. Right? It already is rigged in the situation, does it set equal to 0, that you might attempt to factor it. The problem is that it has trig functions, so we might have to use substitution, right, just to not get bogged down with the details. All right, and we want to know solutions again in this spectrum, this interval, right, of what's possible. All right, notice something. We can sort of temporarily disguise, for lack of a better term, the equation to make it look a little bit more like algebra. All right, if you see, if it's the same trig function here and here, all right, and one of them is squared, all right, and it's in descending order. All right, and it's a trinomial, right, as it is. It has 3 terms like this. Right? It would be the ideal situation for factoring. And you would say, all right, well, let me just pretend that this is, I'll let cosine equal x. All right, so this will just be x squared instead. X squared plus 3x minus 1 is equal to 0. Right? I would at this point attempt to factor it. In this particular problem, not going to work, but I would still try that first. All right? Try to factor first. All right? If it fails, and it will in this case, use the quadratic formula. You know that when you're using the quadratic formula, what are you doing? You're just paying attention to the coefficients at that point. Anyhow, here's what would happen if you attempted to factor this. All right, let's do it the most brute force way. All right, which is to go, oh, well, it's x squared, so I put an x here and an x here. Then I have to consider the factors of 1 in this case, which there's only one factor of 1, it's 1. If I put a 1 here and a 1 here, multiplied, that satisfies the digit, all right? And if I wanted to make it a negative, I would have to do one of each to be a negative and a negative. But this would be the difference of 2 squares, all right? That would not satisfy this middle term, because if you combine these according to their signs, they would cancel out of existence. There'd be no third term. Even if I wasn't paying attention to that, though. Let's say that I attempted to combine these by maybe changing the signs around, even though that wouldn't make sense. 1 times 1 is 1, and 1 plus 1 is 2, not 3, all right? So here's the problem. This can't be factored. Right. It's prime. That's what you would call it, prime. Prime quadratic equation here. All right. So what are we going to do? We're going to use the quadratic formula, right, as the alternative, which means that the square root ultimately is going to show up. All right. Anyhow, what do we really need to pay attention to when we use the quadratic formula? The coefficient a, which in this case would be 1, b, which in this case would be 3, and c, which in this case would be -1. Okay? And we're going to take those 1, 3, and -1 and stuff them in the quadratic formula. I'm running out of space, so I'll put it here. I gotta save these numbers for my own sake. I'm gonna use 1, 3, and -1 for A, B, and C respectively. And eventually I'm gonna have to back substitute because I have to remind myself this is what x is really cosine. All right. X, according to the quadratic formula, is -b plus or minus the square root of b squared minus 4 times ac sitting on top of, this is fading out, 2a. That might be my dud. Hooray. Okay. Anyhow, I'm going to appropriately position the coefficients of the trinomial we just had that had x's. The algebraic incarnation of this trig equation, if you will. 1, 3, negative 1. All right. In place of b, 3 in 2 places. In place of a, 1 in 2 places. And I really should do that, but negative 1 would go here in place of c. Okay. Then we pay attention to the guts, the radicand of the discriminant is what this is referred to as first. In other words, do the arithmetic inside here. We'll decide whether you get a real exclusively or an imaginary answer. All right. 3 squared is 9. A negative and a negative is a positive. Thankfully, no imaginary outcomes here. And this is 4. This 4 times 1 is 4, and 4 times another 1 is still 4. And this is 2 on the outside here, simplified, plus or minus negative 3. And if I compact this down a little bit further, all right, still simplifying the discriminant here, you'd have, that's going to fade, negative 3 plus or minus the square root of 13, which is a terrible number. But that's what it would simplify to. Okay. All right. Now, this is what x equals, all right? All right. We had decided that x was standing in for cosine a long time ago. So what we can do is end up writing a teeny tiny little equation, all right, that gives us the answer, all right, using this as the argument, all right, well, or part of the little equation is what I should say. It's not the actual angle. Here's what we would do, all right. If x is really standing in for cosine of theta, if x is really standing in for cosine of theta, which is very faint, and I'll try to make it a little bit darker, all right, then that means that the cosine of theta is equal to all of this junk, all right, negative 3 plus or minus the square root of 13 on top of 2, so you'll get 2 answers. I'll rewrite this. X, just writing it on the opposite side, is negative 3 plus or minus the square root of 13 sitting on top of 2. Right. Okay. Now, because this is a combination, right, that no matter which way you slice it, is not going to be a special right triangle. Right? You have the square root of 13 in hand, you cannot factor it. All right? What you're going to do is use your calculator ultimately. All right? But just bear in mind, you're going to get 2 answers here. All right? You are going to basically use the inverse cosine. But you're going to have the situation where you have these 2 things being subtracted. All right? And then a second one where you are adding the square root of 13. So let me write this twice. Okay. In one instance, you will set your calculator to the inverse cosine and then input this. Negative 3 minus the square root of 13 over 2. And then in the second instance, negative 3 plus the square root of 13 over 2. If it's in degree mode, it's probably going to give you a highly precise decimal that is degrees, right? So, you know, see 2-digit number, probably maybe a 3-digit number, and you're going to round it, right? As long as it's in this spectrum, that it is under 360 degrees, it's totally fine. So we'll do that. So clear out here. It's getting a little dark. So inverse cosine. I would be very anal about how you enter this, so be careful. All right, if you want, you could use a lot of parentheses, which can get a little cumbersome. So what I'm going to do is I'm going to opt for the fraction style of writing this. No, quit. Alpha and then F1 gives you the numerator denominator. If you didn't go that way, you can get it through the math button. Let's see. The top is going to be the top here, right? -3 minus the square root of 13. Uh-oh. There you go. See how that enters nicely? -3 minus the square root of 13, and then intuitively there is a denominator of 2, and then close parentheses. All right, and see what it spits out. Enter. Ooh, it gave me an error. Let me just check what it did here. Okay. Mode. All right, and then radian degrees. Okay. Oh, I have to switch the mode. Okay. Since you are using an irrational number here, all right, set it to radians, all right, unfortunately, all right, to circumvent any issue. If it gives you an error message, all right, it probably means that you have to change the mode. I had it in degrees, and I really feel it should just do that automatically, but let's see what happens if I switch to radians. All right, quit. All right, and go back here and duplicate that. All right. Oh, still give me an error. What am I doing? Oh, this is minus. Yeah. I know what it is. All right. Yeah. All right. The reason that I'm getting an error message is because I'm using an inverse function. I have to use an inverse function in order to accomplish this, all right? But the problem is that when you have an inverse function, the calculator automatically restricts the domain, all right? So using the red incarnation of this, where you have, I want to say, a negative square root of 13, all right? It's going to give me, it's going to fight me on that, all right? So this is an instance of where, even though there is going to be a second answer potentially, I'm going to just go with the blue, all right, when I'm using my calculator, all right? And then I'll try to figure out as an afterthought where the other coterminal angle would be, all right? As long as it fits in the same 360 degrees. All right, it's because of domain restrictions for inverses, right, that it's fighting me. So, don't fight me. Here am I gonna go? Okay. Let's see. All right, so here's what I'm gonna do. I'm just gonna go with the positive incarnation of this and see what I get. So plus, okay. I shouldn't have to change anything else except the mode, because I really do prefer degrees. So I'm going to do that now. And that looks like it's legit. Okay. Enter. There we go, thankfully. 72.3 degrees, or 72, about 72.4. Right? Yeah. If you had it in radians, which is fine, it really shouldn't matter, all right, would be 1.26. Anyhow, this produces an angle, which is what we were after, that is about 72 degrees. Since in theory the calculator is going to fight me, all right, because this with the negative here, unfortunately, is going to be producing an error message. That means that it's outside the spectrum that is allowed for domain of an inverse. In order to maintain status as a one-to-one function, you have to limit the domain. Right? Anyhow, what you're going to do is basically see if you can add to this. Let's see if it fits in this range here. If I drew a simple picture, here's 0, here's 90, here's 180, here's 270, here's 360. Is there another angle that is coterminal to 720 in this spectrum? All right, maybe, maybe not. Let's just check. All right, 72 would be something like this. All right, an angle of about 72 degrees. All right. All right. If you were to go another 360, you would be outside of 360. All right. So I guess that's it then. All right. 72 degrees roughly. All right. There would be another angle, all right, that has at least the x dimensions in the same, right? If you figure that this is a positive x, then there would be another triangle, as narrow as it is, this way, all right, that shares that same positive x side, all right? It would be a negative y dimension as opposed to a positive y dimension, but it would have the same radius. So if we're talking about cosine, let's say that you subtracted this from 360 to get the other one that would be here, right? The angle that would be this way, right? 360 is 0 minus 72 roughly would be what? 288, something like that. Yeah, 288. So the angle that would be here that has the same x and r dimensions would be about 288 degrees. In theory, this should have done that, right? All right, but again, because of domain restrictions, the calculator is going to fight you. All right. That's sucky. I wish it wouldn't do that. All right. The only reason that I would bother doing that drawing a picture to figure out what the other possibility would be. This is the one angle, I should say it's about 72 degrees. And then there's a second angle that's in that interval. That would be about 288 degrees. The only reason I would bother looking for the second one is because we're talking about cosine. And cosine is an x over an r value, right? It does not involve y. So even though technically the y value would be here, all right, they would share the same x, and the r's would both be positive anyway. So that technically would be okay. Perhaps this, if the calculator was not fighting us on this because of the domain restriction, all right, would produce that. I'm curious what this is as a decimal purely. All right. Let's see. I guess you're gonna just have to infer that because the calculator will not tell you. All right. One more, and then that's it. This gives you an error message, just beware. The arithmetic and the algebra is fine, all right? It's just because of the domain restriction. All right. It has to restrict the domain in order to be an inverse. Otherwise, it wouldn't be 1-to-1. Oh, God. Okay. I have to split this. I have my work cut out for me in terms of cleaning these. Okay, nice problem. This will be quadratic by factoring. I should have done this one first. 2 sine squared of theta minus 5 sine of theta plus 3. Do remember, if you're not given something that is already set equal to 0, right? It's not general form, all right? Try to make it as such, you know, rearrange the parts, right? And make it so, but you have it already given that way. So again, we're going to try factoring, right? Always try factoring first. All right. Then if it fails, then use quadratic formula like the last problem. All right. When it fails, go for the quadratic formula. This one will actually produce that. Now notice it fits some criteria here to sort of rewrite. Disguise using x. This would be 2x squared. If I say that sine is x, then this would be x squared here. So it would be 2x squared minus the 5 times x plus 3 is equal to 0, right? We could use AC product pairs factoring by grouping. It's not impossible if you're trying to factor this to go directly from what you have here to the factored form of this. You just have 4 parts to tinker with, and you could choose what the signs are as an afterthought. I would not do that when you have a coefficient of 2 here. Anything bigger than 1, I would try AC product pairs. Right. And AC product pairs is basically just saying, all right, pay attention exclusively to what is the A here and what is the C here, right? And try to conceive, right, of what their product is. We're going to call that an AC product. And we'll say, and consider pairs of factors that make that product. Factors of 2 times 3, this is 6. There's a limited amount of them, right? There's 1 and 6, and there's 2 and 3, which is what it came from, right? The reason you would establish a list of pairs of factors is that now we're going to take this thing and split it into a sum or a difference, right? You'll see the benefit of factoring this way in a moment. Let us say, that we went with the 2 and the 3 first, right? I'm going to go with this possibility. 2 and 3, only for the reason that that happens to be something that might later be beneficial to me. I'm just rewriting this junk next to it. These are things that in tandem would have to be this amount, via adding maybe or via subtracting. And they both have x's attached to them, of course. All right. This is squared still. Just zeroing in on this right now. What combination of signs would cause this to get bigger? That is, what combinations of signs, negative and positive, or both the same, negatives, both the same positives, or one of each, would cause adding, essentially. And the reason I know it has to be adding, because this amplifies, all right? It would be same signs. Same signs cause adding, all right? Now, if I want the result to be negative, that means that they both have to be the same negative, all right? That's how I choose, all right? Now, I rewrite the junk adjacent here, 2x squared, and 3. This was a positive. And I'm going to now narrow my focus from 4 things to just 2. You might get mad if you've never seen this occur before. To say, hey, jerk, you know, you just took this thing that was complicated enough as it is, 3 terms, and you made it 4, right? The irony of factoring by grouping is that you would have to do it when it is the situation of 4 terms. And it is actually easier, because the reality when you're factoring a trinomial is that you got to pay attention to 3 things at once. When you're factoring by grouping, you're just paying attention to 2 things at once, right? Namely these 2. The reason that I went with this choice of 2 and 3 rather than 1 and 6, they both would have made 5 somehow, is that this will factor, right? What is the greatest common factor here? Notice that they have a letter x in common. The GCF is the thing that you write on the outside, all right, of this factored form of 2x squared minus 2x. They coincidentally have a letter, maximum of just x to the 1st degree, and a number 2 that they have in common as a factor. So now you figure out what sits here and here. 2x times what would be 2x squared. It would have to be an additional x, all right? You don't have to put the 1s, but that's what it would technically be. 2x times what would be a negative version of itself, minus 1, right? Now I'm going to shift focus from here to here. Hopefully this will factor the same way. We're going to start with writing what is in common, the GCF, on the outside here. They don't have a letter in common, but they do have a number in common. And I would start with this. If there's a minus here, let's put a minus on the outside. Sometimes you have to tinker with designs. If you're doing it truly correctly, you don't really. But check it as an afterthought. And then we figure out what sits here and here. Hopefully it will match this. Negative 3 times what would be negative 3x. Just x, because the sign is already accounted for. Negative 3 times what would be the positive incarnation of itself. Negative 1. What happens here, which is that the junk sitting in the parentheses here and the junk sitting in the parentheses here form an exact match. And if that happens, that's great, because the way that this fact is like this. The way that this fact is that the match gets its own parentheses, just written once rather than twice, because that's actually the GCF here now. And the thing that I personally refer to as no textbook will call it this, the left outs, they get their own parentheses. What I mean is, this is the match, which is x minus 1, just written once, right? And the left outs are the things that are literally on the left of each of these, on the outside of these. They're left out, literally. That's 2x minus 3. All right, what does this still equal? 0, all right? We've done the hard part. We factored. All right? This should be old hat, but if you feel a little sketchy about it, right, there's a technique, all right? And it's exactly what we just did. It's AC product pairs. It's just paying attention to the coefficient in the front and the coefficient, the constant in the back. And they form the product, all right? And whatever that product is, it has pairs of factors that it can make. And if you list every conceivable pair, all right, you will have choices, if you will, for what you will use to decide, well, what makes the middle thing simultaneously, the middle term of 5 in this case. There are sometimes two choices that seem possible, but when you check the signs, it's only one of them that works. And if ultimately nothing works after attempting AC product pairs, that means it's not factorable, and then you would have to use the quadratic formula. Anyhow, this is what we end up with. We have this disguised incarnation of 2 sine squared theta. And in fact is like this: x minus 1 and 2x minus 3 is equal to 0. All right. At this point, all right, we can now reverse the substitution. All right. If we said that x is standing in for sine, then wherever you see an x, put a sign. Right? So you would have this sine here of theta, and 2 times the sine of theta here. That makes this sine of theta minus 1 and 2 sine of theta minus 3, and they still equal 0. And now we're going to invoke the zero product rule. And the zero product rule says that you have these isolated factors here, they're being multiplied. And if they're set equal to 0 here, which is by design, perhaps this chunk, this factor, is 0, right? Or perhaps this chunk by itself is 0. Because whatever that is times 0 would still be 0. Whatever this is times 0 would be 0. Or perhaps both of them are. So, no, reasoning that, you have 2 slightly smaller equations that result. Now using the original trig function. And you go through the motions here and here. Right? Rearrange them. This isn't too bad, right? Scoot 1 over by adding. That means that the sine of theta is equal to positive 1. This one's going to be more of a pain in the neck. Right? Scoot 3 over. Add 3, cancellation effect. And if you have 2 sine of theta is equal to 3, you're going to divide by 2, and then you have that. Right. I need this space, so I'm going to erase some stuff. Okay, so I got this first one. The sine of theta is equal to positive 1. And the second one, which is that the sine of theta is equal to 3/2, right? 1.5. All right. One of these is going to be okay in this spectrum, which I should have specified to begin with. The angle has to be in this interval. Right, basically from 0 degrees to 360 degrees would have to be okay. When you see this one, right? Let's say that you took your calculator and you typed the inverse function of positive 1 to figure out what the angle was. what you're going to get, because this is sine, maximum positive 1, minimum of that. And these points are relevant. That's 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. You could infer to yourself, well, if it's positive 1, in the spectrum of a complete circle, 0 to 360, where is the y value positive 1, right? Right at 90 degrees, right? That much of the circle in, right? It would be negative 1 if you went all the way to 3 pi over 2, and we only want positive, right? So this theta has to be pi over 2, right? Which, if you use your calculator, would probably just simply say 90 degrees, right? Let's verify. The inverse sine of 1, right? Typed into your calculator like so. It's in degree mode, so you get 90, right? That's that point on the sine curve. Right there is when y would be positive 1. And the reason I'm calling this y, because theta is normally the x. I mean, it's the input. This is the input, this is the output. Not to be confused with the x we used before. All right, now this one is probably going to get in trouble, right? Because if you use the inverse function on your calculator, you're dealing with a domain restriction again. All right, so it might give you an error message. We'll check, and if it does, we'll draw a picture to figure it out. All right, 3 pi over 2. We'll give you the angle. Just bear in mind that this is really what number, right? This is 3 pi, pardon me, it's 3 divided by 2, which is what is a decimal, right? If it's 1.5, it's 1.5. What is the maximum allowed to be? The maximum is 1. So that's probably a bogus answer, even though that's the way the arithmetic works out, and the algebra as well, all right? Because you can't go beyond this on our standard sine curve, all right? There's no coefficient here that makes it different, all right? That makes the amplitude larger, all right? Nothing makes the amplitude larger here. So this is probably going to be a dud, all right? Not your fault, all right? You are never going to get bigger than 1, all right, given this situation, all right? 1 is the maximum, all right? Or if it's a negative 1, that would be the minimum. This is beyond that, 1.5. So be suspicious that this is not going to work. And perhaps when you attempt to use your trig function, it's going to give you an error message. We'll see. All right, 3 divided by 2, all right? Okay, yep, error message. How come? In the context of a regular trig function, right, this is a y, which means it's a range, right? And the range is restricted between negative and positive 1. Those are the maximum and the minimum. It will never stretch beyond those two. An inverse function, which is what we're using here, has the x's and y values switched, right? So what was the range of one becomes the domain of the other, right? This gives you an error because of a domain restriction. Right. It's a domain in the context of an inverse, okay? So, only one answer, pi over 2. Okay, 90 degrees. All right, that is it. All right. Thank you guys for listening. This is running a bit long, but that's pretty much everything that you would see. All right, and the homework that you would want to take a look at is section 9.5. All right, so I'll give you a link as soon as this uploads. All right, thank you, and stay safe out there.